Does it now say recording on your screen?
Does on mine.
Good. Okay, so this is our schedule for the day, for today. I should tell you that all of the modules that we'll be presenting today are in the Dropbox that Kurt has shared the link. I'm sure you've been there before, accessing all of the hands-on materials. So our PowerPoint modules are on there also. You're welcome to download those. You can use them through the session today. You're welcome to use them forever in your courses, preparing for your prelims, whatever teaching courses that you are involved in. You're welcome to use these modules however you want. We're giving you the PowerPoint version so you can take material and move it around however you want to do it. So here's our flow for today. We're going to start off with 3 modules with geochronology. They're about half an hour each, something like that. And we'll do a little bit of Q&A between each one, and definitely jump in the chat function as we go if you have questions. There's also a couple of polls that I've put in here that we'll be working through. We'll take a little break, and then we're going to do some hands-on work with data reduction and uploading to Geochron. Then we'll have lunch midday. This is sort of on a Tucson schedule anyway. And then we'll dive into 3 modules after lunch here: quantitative analyses, a hands-on activity. We'll talk about theory and applications of lutetium hafnium geochemistry. We'll have a break, and then we'll do some more hands-on work with hafnium plotter, and we'll end up talking about trace element geochemistry, and then we'll have some wrap up at the end. So that's our plan for today. Unless there's anything that we should address up front, let's just go ahead and dive into our first module. And I'll stop here for a second and see if there's anything coming in on the chat that we need to address.
I think we're all set. Sarah and I
are happy. Hope everybody has some coffee ready to go. Okay, we're going to start off from kind of ground zero, which is the isotope decay systems of our parents, uranium and thorium, decaying to our daughter product, lead. And fortunately, in contrast to many other radioactive decay systems, these systems are pretty simple. There's no significant branching or interferences in any way. It's pretty simple. We start off with a parent here, uranium-238. And this is the first reaction that takes place. This is kind of the statistical part of radioactive decay. And this is the one that controls the rate of decay of this system. So this is the rate controlling one. This is like the faucet on the hose that determines how fast uranium-238 is going to decay down to lead-206. All of the other half-lives are shorter. So this it's a pretty simple system. Every atom of 238 that decays ends up as lead-206. So it's a simple system. There is a little bit of a complexity that thorium-230 is in the decay system. And as you know, there's an isotope of thorium-230 that's naturally occurring also. And so in a mineral like monazite that has a lot of thorium, you might get a little bit of 230 from the decay of that thorium, which then also contributes to 206. So you could have a little bit of extra 206 if there's a lot of thorium present in your mineral. For example, for monazite, young samples, you need to do a bit of a correction for that. But for zircon, for most older systems, no problem. It's a simple decay system. And the half-life, this is the important part, it's about the age of the Earth, just by coincidence. 4.5 billion years is the half-life. And so here's our second decay system, that uranium-235 decays to lead-207. It has a much shorter half-life, about 700 million years. And this is going to be really important. I think this is an essential part of understanding how geochronology works, is that we have 2 different chronometers, 238 and 235. It's like having 2 watches on your arm, and they're ticking at different rates. And that's a really powerful aspect of the technique. One is more powerful for younger systems, and the other one is more powerful for older systems. So we'll talk a lot about that this morning. And then here's the third one, thorium-232 decays to lead-208, and this has a very long half-life, 14 billion years. So we'll kind of explore those 3 decay systems in these next plots. But first, just to kind of rub your nose in the decay equation and the age equation, we don't need to work our way through this today, but maybe when you're preparing for your comps, you might spend a little time going through this slide here and just make sure you understand how that derivation works. But it basically is just the fundamental process of radioactive decay, that the rate of change of a parent atom is a function of the number of the parent atoms. And so you've seen this before in a classroom setting where you start off with parents, and then after one half-life, half of the students have to sit down. After the second half-life, half the students. So it's proportional to the number of students who are in the classroom. And so we end up here with the equation that the number of daughters is proportional to the number of parents, kind of going back to this idea. And then it's lambda, which is the decay constant. That's just kind of the probability that a decay is going to happen. And time, of course, that's what we're interested in. And then this would be the decay equation, where it's daughter to parent. That's the important ratio that we're going to be working with. And then it's e to the lambda t minus 1. So just basics of how that decay equation is derived. So here's how it works. This is sort of a fun example if you're especially into bike racing, although this view right here might be a little scary, seeing a bike over people's heads. But here's how it works. If you start off at a bike race in the morning, you know the number of riders. And then during the day, you know the number of people that have crashed during that bike race. All you need to know to figure out how long that bike race lasted were these three things: the number of riders, the number of crashes, and the probability of a crash. And this is probably what your mom told you before the start of the bike race. Darling, don't go racing today. The probability of a crash is lambda. So your mother probably told you that. And then if you have those three things, you can just change the decay equation to the age equation. Time is lambda, parent over daughter, and the decay constant. So that's how we could use this as kind of a real world example for us today. But let's look at how these systems work in diagram space here. And we're going to start off on the left for 238 to going to lead 206, again, a long half-life. We're going to do this in terms of time now. So we're going to start at the age of the Earth. The Earth just forms. We have a zircon crystal. It starts off here with a lot of 238 uranium, 100%, and no lead 206 because there has not yet been any decay. As time goes on, we start off 1 billion years, 2 billion years, and so on to the present day. And because the half-life is about the same as the age of the Earth, you end up in present day with about equal atom, 238, 206, so a ratio of 1 for 206, 238. But the rate of change here it's exponential, but we're only one half-life out. So it almost looks kind of linear, and that's going to be important as we move into the application of this system. So here's the important thing, is that 235 to 207 is very different. It starts off with a very short half-life here. It starts off again, of course, with all 235 and all 235 and no 207. And then this 235 decays rapidly, right? By the time you get to 704 million years, you're already at equal atom, parent and daughter. And then it continues on, and there's just less and less parent and more daughter, but the rate of growth of that daughter is not so fast here, and the rate of decay of the parent is not so fast here. So this turns out to be really powerful. This is what makes the older part of Concordia, the application of uranium-lead geochronology to Archean systems, so powerful. We can determine very precise ages because there was so much 235 early in Earth history, and it was decaying rapidly to 207. And then our third decay system here, 232 thorium going to lead 208, very long half-life. And you can see this one is just about a linear change through time. So that's how we do it through time, but that's not really of interest to us, right? More interesting for us is how we look at these patterns as a function of age. So here's how now we're changing that decay equation, and now we're looking at this in terms of age. We'll start off left, 238 to 206, same half-life. And now here's how it works. If we're at the present day and we're looking back in time, here's how that ratio of 206 to 238 is going to change as a function of age of the zircon crystal or whatever mineral we're interested in. So because the half-life is about the same age as the age of the Earth, if we have a zircon, maybe from Jack Hills, that's 4.5 billion years old, wouldn't that be nice if we could find one of those? It would have equal atom 206 to 238 because that's the same as the half-life, right? Okay, so here's what's very different is that 235, 207, it's not changing very fast right now, so this is not a very powerful tool for young systems, but as you get older, look at how fast this 207, 235 ratio changes. When you're back here in the Hadean, it's changing really fast, and there's a lot of 235, there's a lot of 207, so this is where the 207, 235 chronometer becomes really powerful, very precise. And the curve of this line here is what's going to show up in our Concordia diagram to give it the curve that we observe. So we'll come back and talk about this. And then, like we said, the thorium lead decay system is just about linear. Even for a 4.5 billion year old zircon, you still don't have very much 208 relative to 232 because the decay constant is so, the half-life is so long. So I hope that's good for everybody. Kind of the basics of how the systems work. Okay, but guess what? It's actually a little bit more complicated or even more powerful than that, in that you can also determine the age of a crystal just by looking at 206 and 207. So that's kind of puzzling. We're talking about uranium-lead geochronology, and I'm telling you, you can determine the age of a crystal just by looking at the 6-7 ratio. You don't even need to measure uranium. And just to show you how this works, let's do some quick math here. Here's the decay equation. 206 is produced by the decay of 238 through the decay constant as a function of time. And you take the same thing for 207, 235.
Hello.
Yes.
Good, how are you?
Good, what
Oh, yeah.
Okay, so what we're going to do is we're going to take the 206, 238 system and divide by this one, right? So blue over red. Same thing over here, blue over red. And then we're going to start to rearrange this a little bit. We've got 238 and 235. How about if we take that out and just make 238, 235 here, times the decay part for 238, decay part for 235, right? So just rearranging a little bit. And now it turns out that we know this ratio. Any material on Earth, well, almost any material on Earth that you measure today is going to give you this same 238, 235 ratio. This is one of the magic numbers of geochronology. This is one of the ones you need to carry around in your head. 137.82 is the modern ratio of 238 to 235. Well, so guess what? We don't have to measure this because it's fixed in nature. So let's just sub in 137.82. And now we've got measuring 206, measuring 207. We know the half-life for 8 and 5. And what you can do is you can solve this for T. It's transcendental. You need to iterate this a few times, but it's easy to do on a calculator. So here's how this chronometer works, is that we can measure 6-7 ratio. We know the ratio of 238, 235, and you can just crank out the age of that crystal. And here's how the 6-7 ratio goes as a function of time. If it's a very young, as a function of age, very young system, you get a high ratio, about 20 something. As that crystal gets older and older, the 6-7 ratio decreases because there's more 207. Okay, so we have these 4 different chronometers, not just 3. 68, 75, here's the new one, 67, and 208, 232. And the question is, which of these chronometers are we going to end up using? Which is the most powerful one? And that's a complicated question that's going to take us some time to work through that. So, but first let's look at this in terms of isotope space. We'll go to this diagram, which shows kind of schematically how much 238 is going to be in your mineral that you're measuring. 235 is always less, 232. And it shows how 238 decays to 206, 235 decays to 207, 232 decays to 208, right? So this is just what we've shown now in a slightly different way on the isotope spectrum. So that's all great, but look at this. It turns out when you're on your mass spectrometer and you're measuring lead 208, 207, 206, you also will be able to measure some lead 204. It's a small amount. There's usually much less 204 than any of these other systems, but it's always there. There's always 204 in every mineral that you'd analyze. So what does this mean for us? And I know you're thinking about this. Wait a minute. This 204, it's not a product of decay, right? There's nothing that's decaying to 204. So that means that that 204 must have been there when the crystal formed. This would be back at time 0. And that would make you wonder, well, if there was 204 present at time 0, was there also some 206, some 207 and 208? And the bad news is that yes, every zircon crystal that you have, every mineral you measure, has some 206, 7, and 8 that's initial. It was there at time 0. And so the question is, that means my ages are 2, and let's see if we can pull up that poll. We're on the second. Hang on. Here we go. I'd like everybody to check in on the poll here. Uh-oh, my ages are too, what's it going to be? So if you're still thinking about this, here's some 204 in your crystal. That means there must be a little bit of 206, a little bit of 207, a little bit of 208. That's initial. It's not caused by the decay of uranium and thorium. And so the ages that you calculate, if you don't subtract that 204, are looks like we're a little over halfway there. Let's get everybody clicking in here. I'd like everybody to vote. It's voting season. Let's vote. All right, looks like we're kind of stable at 32 out of 44. So not everybody voted. I'll share the results with you. Here's what the polls tell us. Looks like red is about 64%. It's too old. And so a few people think that it's going to be too young. So let's see if we can figure this out. So you're in your crystal today, you have some 208, 207, 206. Your mass spectrometer can't tell the difference between red 206 and black 206, right? There's going to be a little bit of black 206 down here. So if you don't subtract out that black 206 and you instead use that whole red bar, you're going to have a lot of 206 relative to 238. You're going to calculate an age, and that's going to be too old. If you were to subtract out that black 206, the initial 206, then your age would be a little bit younger. So the answer is that your age is going to be too old. So you have to do this 204 correction. You have to subtract out this common lead from that analysis. So here's how it looks. Here's the 204. Here's the 6, 7, 8, and I've kind of exaggerated this. It wouldn't be quite so large. It's not like 10% is going to be 206. It might be a much smaller percentage. But this is what you have to subtract. And so the question is, how do you know how much 206, 207, and 208 to subtract? How do you know what the ratio was back at the time of crystallization of 206 to 204, 207, 204, and 208, 204? So you want to jump in and just chat? Tell me, how do you do this? How do we know how much 206, 7, and 8 to subtract from our measured values to do this correction for common lead? Sarah, maybe can you read the chat?
There has been nothing said, but I would be happy to read it. Oh, now we've got chondrite as an option.
Do chondrite, yeah, look at chondrites. What else? I've given you a hint over here on the right. What is that flashy gray crystal in the upper right here?
Galena.
Galena, what do you know about galena? What's galena? What's the formula?
Lead sulfide.
It's got a lot of lead in it. And there are ore deposits that you can go to around the world. And imagine if you can find galena crystals in an ore deposit that's like Archean in age. What you could do is you could measure the lead isotope ratio of that galena that's Archean age. And that probably hasn't changed very much, right? There's not a lot of uranium in galena. And so the lead isotope composition of a galena crystal back in an old ore deposit hasn't changed at all. So this would tell you what that 2064 ratio, 74, 84 ratio was back at various times in the past. So this was done back in the 70s. Some really smart USGS geologists did a survey of ore deposit galena from around the world, and they made a lead evolution line. This is the evolution of lead isotope composition through time from the Hadean to the present day. So we call this the Stacy-Kramer's curve for the authors of that paper in 1975. And this is what we do. We just subtract out 6,4. We measure 204. You got to measure the 204, but that's easy, right? Because there's no radiogenic 204. It's all initial. And you subtract out 6,4, 7,4, 8,4, depending on what Stacy-Kramer's values you have. And that's how you do this common lead correction. And this is absolutely essential for high quality geochronology. If you don't do it, here's the bad news. And we're going to do this for two different age systems. We'll look at this first for 206, 238 ages. And it's a function of the age of the crystal that you're interested in. So if you do young samples, 10 million, 100 million, a billion, 3 billion, you're going to have slightly ages that are slightly too old as a function of age, and also as a function of just how much common lead there is in that system. And so if you're over here on this side, where there's a lot of that black 206, 207, and 208, your ages are going to be off by 1%, 2%, 3%, and they're all going to be too old. If you don't measure that 204, you won't know how much too old they are. They're going to be too old. Your ages are going to be off by a few percent. For 206, 207, it's even worse, especially for really young systems. For 3 billion-year-old zircons or minerals, not so bad. Regardless of how much common lead is in there, it's not going to make much difference for old system. If it's a billion years, we'll look at this. You're going to be 20% too old, 30, 40, 50, 60. If you're looking at a Phanerozoic sample, 500 MA, you're going to be 100% too old. So this is really bad news. If you don't do this common lead correction, every age that you calculate from your sample is going to be too old, and you won't know how much too old it is because you don't know how much 204 is in your sample. So this is kind of like recommendation number one when you're going to do uranium lead geochronology, is to make sure that you're able to measure that 204 concentration correctly. And this is actually one of the most difficult things to do with our mass spectrometers, is measure that lead 204. Okay, so let's go back and look at our 4 different chronometers. That common lead correction, that was kind of like our first bump in the road, our first complexity. Now we've got the 3 main systems that we're going to use for zircon. If we had a session today on monazite, then we would be using this one, but there's not that much thorium in zircon, and so we generally don't use that. The powerful thing about these 3 decay systems is that you can show them all on a single diagram. And I know you've seen this before. This is the Concordia diagram. And you're saying, yeah, okay, I see 2 of them. I see 206, 238 over here. And so the way that you would use this axis is, as time goes on, you increase 206 to 238. You go up the axis this way. And the age that you calculate just gets progressively older and older and older. Likewise, for 207, 235, that ratio is going to increase in time, right? As time goes on, you develop more 207, less 235. And so the 7.5 age increases as you go out that way. And the Concordia line, this blue line here, this is just the intersection of those 2 different chronometers as a function of time. So if you're right here, 2.8 billion years ago, that's the age that you would calculate from the 6:8 ratio, and that's the age that you would calculate from the 7.5 ratio. Now, the important thing to note on here is look at how the curve expands out here back in the Precambrian, especially in the Hadean. It really gets sensitive to time. It really separates out. And that's because of that really rapid decay of 235. Remember, early in Earth history, lots of 235 decaying rapidly. So this is the powerful part of Concordia for the 207, 235 system. 206, 238 system is more powerful down here because there's not very much change in 207, 235. Good? So that's 2 of the ages, but wait a minute, where's the third? The third one we're looking for is 206, 207. We'll get to that in just a second. So here's how this works. We're going to start off with a magma crystallizing here at time 0. If we sit around and watch this for 1 billion years, 206, 238 is going to increase. Here's the ratio you'd measure, the age you calculate. Here's the ratio you measure for 7.5, the age you calculate. Here's where you'd be 1 billion years later, 2 billion, 3 billion. So the dot just moves out along Concordia. We call this a concordant analysis if it sits on top of Concordia. Okay, so here's where our third chronometer comes in. 6.8 is easy, 7.5 is easy to read off the diagram. It turns out that the slope of the line from the origin to our analysis is proportional to the 206, 207 age. So we're just going to take rise over run, 6.8 over 7.5, rearrange the terms, 6 over 7. We know 238 over 235. So here's what we did before. This is how you get rid of uranium from that decay equation. And you would end up calculating the same age here, 2.9 billion years old for 6.7, 7.5, and 206, 238. So here's our poll number 2. Which of these ages are you going to use? We don't need all 3, right? If we're trying to determine where that position is in Concordia space, you don't need to measure all 3. You only need to measure 2 of them. So which are the obvious 2 that you're going to measure, knowing what you do about this decay system? So let's go to poll number 2, and here we go. So the question is, which are the 2 ages that you're going to use to determine the position on Concordia?
Pardon, excuse me, do we select the one that we're not going to use?
Yeah, I know the question is a little different from the title of this. So let's just answer the specific question. Which 2 ages are used to determine position on Concordia?
It will only let me select one, so.
Okay. Well, I'm sorry, I had the poll not quite set up right. This is the question I wanted to ask here. Which one is not used? So let's change this. If you haven't done it yet, which one is the one you're not going to use? All right, looks like we're getting most people in. I had this set up correctly yesterday, and this morning I went in and just did a little fiddling, thinking I was going to make it simpler, and I guess I made it more complicated. Sorry about that. So end polling, and because I messed up the question, maybe this is not so useful, but let's just kind of think about it with these 3 up here. You got 6.8, 7.5, and 6.7. Everybody agrees you're going to do 206, 207. And the question is, between these 2, which are you going to use? And 238 is probably the one that you want to use. And that's because there's so much more 238 than there is 235. How much more 238 is in your crystal than 235? What's that magic number? Yeah, 137.82, right? So there's lots more 238, not very much 235. So you probably want to use these here. Okay, sorry about that. I'll try to get the next ones right. So here's how it's going to work. We're going to use the 206, 238 system because there's a lot of 238 present. We're going to use the 206, 207 system, and we're not going to use the 207, 235. That's kind of counterintuitive. This is one of our main decay systems. 207, 235 is the other one, but we're actually not going to use 207, 235. We're going to use 6.7 instead. And that's because there's very little 235. You don't actually need to measure 235 because you know what it is. 238, 235 is 137.82. So you just calculate it. You don't need to measure 207, 235. So you just measure 207, 206, and this is the one you're going to use. If you wanted to calculate it, here's how it would work. 207, 235 is just 6.8 over 6.7 times 137.82. And that's what your 207, 235 ratio would be. Well, you're thinking, well, if those are the 2 ages that we're going to use, why don't we use those as the axes on our Concordia diagram? And that was suggested back in the 70s. Tara Wasserberg came up with this kind of alternative Concordia plot. And now here's the 6.7 age on the vertical and the inverse of 206, 238 on the x-axis. And here's our Concordia line. And this works exactly the same as the traditional Concordia diagram. It's got exactly the same information. You would just measure 6.8, calculate 2.9 billion, measure 6.7, calculate, you define your point on Concordia, and off you go. It just turns out that this one is not so simple to use, especially because of this big expansion of age here as a function of 206, 238. And that's because 6.7 is not changing very much for young systems. So we generally don't use this, but you might see this in maybe 10% of the papers that are published with uranium lead geochronology. Okay, so let's talk a little bit about the uncertainties of these two different age systems, the two we're going to use, 6.8 and 6.7. And it turns out that in terms of precision, we know exactly how this works. And here's how it is. This ellipse here, this would be the uncertainty envelope for an analysis that's about 2.9 billion years old. And what you can see is that the uncertainty for 206, 238 from here to here, right, going over on the left, that's a pretty big uncertainty. It's probably, maybe 100 million years of uncertainty. Whereas our 6.7 line, the line from the origin through this point, that's pretty well constrained. There's a lot of 207 to measure, so we can get this very precise. So for 206, 207 ages are probably the ones to use. They're the most precise for older systems. And down here, 206, 238 is quite precise for young systems, whereas 207, look at this big uncertainty for 207, 235, or 206, 207. So this is the one you want to use. And it turns out right in the middle of Concordia space of geologic time, this is the time area where neither one is very precise. And so this is actually our toughest part of geologic time to work in with the uranium lead system. And this is kind of a blast of data, but see if you can kind of step back and just focus on the main pattern. What I'm showing here is age on the X and the uncertainty of that age that you would calculate on the Y-axis. And this is in millions of years, not percent. And so what it shows you is that for young systems, look at this, you can calculate very young zircon ages with only 1 or 2 million years of uncertainty. As you get older, the percent uncertainty stays the same, but the amount of time of uncertainty, 30 million years, 40 million years, increases. So this is not very precise for 206, 238. 206, 207 is exactly the opposite. Look at this, for 206, 207 of an Archean zircon, 2.8 billion years old, I can tell you that age with an uncertainty of less than 10. I can tell you some of these with an uncertainty that's like 2 million years, 0.1% uncertainty. So the 6.7 is really precise out here for old systems, but then the uncertainty just explodes, when you go to younger and younger systems. So this is the curve, the diagram that tells you which ages you want to use. You want to use 206, 238 for young systems. You want to use 206, 207 for old systems. And this is the bad news, that neither of these systems are very precise for middle-aged zircons, Proterozoic zircons, 1.0 to 1.6. This is the toughest part of geologic time for us to work in the uranium lead system. Okay, so that's one of the sort of essential things that you need to know is which of these two ages you're going to use with your data set. Unfortunately, there are a few other complications that we have to talk about in the uranium lead system. And let's just kind of jump into these and go through them quickly. We have complexities, 3 different complexities. You have one from lead loss, inheritance, and overgrowths of zircon crystals. And here's how the first one works. This is lead loss. And let's imagine that we're starting off right here at time 0. We grow a zircon crystal, we wait for 2 billion years, and that zircon crystal ends up out here. And now we're going to come along today and we're going to hit that zircon with some hydrothermal fluids. And it turns out that the toughest fluids, the toughest kind of temperature conditions for zircon are about 300, 400 degrees C, like green schist facies. This is really effective at removing some of that lead. Turns out lead is not charge bound in the crystal. It doesn't fit very well in the lattice. And so when you pump fluids through a zircon crystal, it's going to remove some of the lead. Probably not the uranium because it's charge bound and it fits well. So as you remove that lead, you're going to move down this line, right? If you remove 10% of the lead, you'll be here. If you move 50% of the lead, you'll be here. And so this is what we call lead loss. It removes both 206 and 207. It's a pretty simple pattern that smaller grains tend to lose more lead, and that's just because there's more surface area to volume on that crystal. And also high uranium grains tend to lose more lead than low uranium grains, and that's just because of the radiation damage. One of the magical things about Concordia diagram is that now if we stop and we sit here for another billion years, that line remains straight, and so the upper intercept of that line is going to be the igneous age when that zircon formed. And the lower intercept down here, that's going to be the age of hydrothermal activity. So you could analyze this by looking at bigger crystals and smaller crystals, low uranium, high uranium, or nowadays with CL imaging, you can actually do this on an individual grain. The dark areas of CL tend to be high uranium, so they might be down here. The lighter areas here and here have less uranium, they would tend to be up here. So you could actually generate a line like this and get 2 ages just from a single zircon crystal by placing your analysis spots in different places. But here's a great way for analyses to end up down here below Concordia, and we call this a discordant analysis. Here's our second complexity. It turns out that zircon commonly can be inherited into younger magma. So this would be a zircon that crystallized at one time period, and then we form some new zircon around the outside of this. So this would be older zircon and younger zircon. This might happen if you crystallize a magma today by melting of some sedimentary material around it that contains old zircon. So this would be zircon in the country rock. The magmatic zircon is going to grow over those older cores of inherited zircon. And now the magic of Concordia is that line remains straight. And so if you were to put some analysis points here, you might end up with the crystallization age. Put some points in here, you would end up with the inherited age. So this is kind of the power of CL images. For every analysis, you really should look at these images and figure out where you want to put your analysis spot, whether you want to get the inherited age or the crystallization age, or better yet, get both. And you can get a very similar pattern in terms of CL images from metamorphic overgrowth. Zircon also grows during metamorphism. And so you could have a situation where this is the older material, igneous zircon perhaps, and this would be younger metamorphic zircon that grows around the outside of that older material. So this is not inheritance, this would be metamorphic zircon growing around the outside of an older material. And unfortunately, there are ways we can tell metamorphic from igneous zircon. High uranium thorium generally is characteristic of metamorphic zircon. Low uranium thorium might be igneous. So you can tease out this pattern by doing spots in different parts of the crystal and then looking at the ages and uranium thorium values. So let's see how this plays out with a detrital zircon data set. This is just a set of a few hundred analyses from a sample, and you can see this was an interesting sample because it's got zircon ages that are quite young, middle age, and quite old. And you can see that lots of these analyses are right on top of Concordia, and if that's the case, then life is good, right? There's no ambiguity about the age of that zircon crystal. But what about this one? What would you say is the true crystallization age of that zircon? And that's really tough to tell. It's actually impossible to tell. You've got a lot of degrees of freedom. It could be this old, having been pulled down by lead loss, or it could be this age and having been pulled up by inheritance. And so if you have an analysis that's way off of Concordia, way out here, it's really tough to be sure what the true age of that crystal is. The closer you are to Concordia, the fewer degrees of freedom, the less uncertainty there is about that age. So this is something that you have to determine as the owner of this data set, even though the data might be generated in a lab where they know a lot about the individual analyses. You're the one that has to decide which of these analyses you're going to use or not. So the way we do this is by calculating how discordant your crystal is. And we do this with this convention that we look at the 6-7 age and we divide it by the 206-238 age. So here's 6-7 age, right? Here's the 638 age of that analysis. The ratio of those two just gives you the percent. This point would be 25% discordant or 75% concordant. So that's pretty far off of Concordia. You probably wouldn't want to use one that's 25% discordant. Well, so what kind of a cutoff are you going to use? Are you going to say, well, I'm only going to take analyses that are less than 10% discordant or 5%? What is the cutoff that you're going to use? And here's sort of some rules of thumb for this. If you use a really tight filter, that you're only going to take analyses that are concordant or up to 10% discordant, so within 10% off of the Concordia line. Those are really good for accuracy, but it turns out that your age distribution is going to be biased. And that's because these older Archean zircons are probably going to be more affected by lead loss than younger ones. So you might actually get rid of most of your old analyses if you apply that tight filter. In contrast, if you go to a very loose filter, maybe we're going to accept all of these analyses. Well, for those out here far from Concordia, the ages are not very accurate. But the good news is that your age distribution is going to be less biased. So here's the punchline, is that you need to understand enough about concordant versus discordant analyses that you are the person who makes that decision. What is going to be the cutoff for acceptance of discordant analyses? Are you going to hang really tight and get the most accurate ages you can, but realize your distribution is going to be biased? Or are you going to open up the filter and say, hey, let's take everything, and then it's going to be less biased, but the ages are less accurate? So this is why we really encourage you to go to the lab, be involved in generating the data so that you understand the issues of discordance. So just to kind of recap, when you have concordant zircons, the decision about which one you're going to use is pretty simple. It's the blue values here. If you're older than 1.4, you're going to use the 6-7 ages. If you're younger than 1.4, you want to use 206-238 ages. It's a little different when they're discordant. It turns out that 6-7 ages are a little bit more accurate than 6-8 ages. And so we would use a cutoff more like 800 or 900 MA. This also turns out to be a good cutoff because in the world, there are not that many crystals that are about 900 million years old. And so you can separate your data nicely into older and younger ones by using a cutoff of about 800 or 900 million years old. So we'll kind of end up here. These are some of the best practices that you need just to understand kind of the basics of geochronology. You need to understand how all these three age systems are calculated. You need to realize why we use 6-8 and 6-7, but not 7-35, because we don't need to. We know 137.82. You have to subtract out the common lead using 204. And, you know, I guess I would kind of take a hard line on this and say that, you know, if you're not able to measure 204, I just don't think that you can do high quality geochronology. There's 204 present in every crystal that you measure. You need to be able to measure that, or your ages are just going to be too old. You won't know how much too old they are because you haven't measured that 204. Need to know how to use the Concordia diagram. That's how you're going to present your data. You need to know the precision of these 6-8 versus 6-7 ages so you can choose which one you're going to report. And then you need to understand that patterns of discordance, those three main processes. CL images are an absolutely essential tool for doing that kind of analysis. You need to be able to see where the spot is in each grain to understand that discordance process. Then you're the one that has to set this filter, 10%, 20%, 30%. Most papers these days are in the 10 to 20% range. And you also need to set that cutoff for 6-8 versus 6-7. So this is why it's so important for you to be engaged in the generation of this data, is that you need to make some really important decisions about how your data are going to be processed and reduced and plotted and analyzed and then eventually interpreted. So I'll stop there for just a minute and see if there's any questions. This was the end of module number 1. I'm sorry, I haven't been able to see the chat function. Looks like you've had lots of good discussion. Are there any questions that we should deal with in person? If yes, just jump on with your audio and fire away. We'll probably spend 5 minutes doing this and just see if there's any questions or issues that come up.
George, there was a question early on about the decay system, and I think essentially how we know the half-lives of the different decay systems.
Yeah, that's actually a really interesting question. And this is something that the young Earth folks are very set on. How do we know those decay constants? And traditionally, it's been done in a very simple way. You just take a lot of uranium and you put it into some kind of amount and you measure the alpha and beta decays that are coming off of that material. And if you know how much is there and you can count the decays, then you can figure out what the half-life would be. It's just a probability of individual atom decaying in a unit of time. So that's all done strictly by measurement. There's no interpretation. There's no belief in that. That's something that we can just straight up measure.
Hi, I do have one question. How can you deal with common lead corrections when you're working on LA ICP-MS and you don't measure 204 lead, although you measure 204 counts? Like you said, there was like the 206, 204 ratios could tell us how bad is common lead affecting your data. So after that, how can you work that out with the laser ICP?
Yeah, so that the measurement of 204 is probably the most challenging measurement that we make. That's kind of ironic because we're really interested in 6, 7, 8, 235, 238, and yet we actually have to work really, really hard to measure that 204. As I tried to kind of show with the diagrams, though, it's essential that you do that. So this is one of the most challenging things for a lab, to be able to measure 204. And I would say if you're not able to measure 204 accurately, then I don't think that the data are going to be as good as they could be if you're able to measure 204. So for laboratories, I would say you need to work hard to be able to measure that 204. It's actually even more difficult than just measuring that 204. With a plasma instrument, you're putting a lot of argon and helium into the front end of the machine. There commonly is a fair amount of mercury, especially in helium, and mercury has an isotope that's 204. And so when you're measuring the 204 peak in your sample, it's actually both lead 204 and mercury 204. So not only do you have to measure 204, you also have to measure 202, which is the isotope of mercury that is independent of lead. So this is very challenging. I should also mention that there are other ways to do that common lead correction. You can do it with 206, 207, but that requires the assumption that your analysis is concordant. If it's discordant and your point is off the curve, it could be due to inheritance, it could be due to lead loss, it could also be due to the common lead correction. And so if you ever use the software called Iolite, they have a tool in there that allows you to take your analysis and slide it back onto Concordia with that common lead correction. I don't recommend that as a good practice because it is doing a common lead correction, but that discordance could be due to inheritance or lead loss. So then there's a third way you can do it. You can also use the thorium lead age, 28232 age, compare that to 68 age, and use that to figure out how much common lead is in your crystal. Those two methods, though, require some assumptions, whereas the 204 method does not require any assumptions. So I think this is this might be a bump in the road for people doing uranium lead geochronology. And in my view, you just have to measure 204 accurately to do high quality uranium lead dating.
Okay, thank you.
Okay. Let's go on to module number 2.